And so we're looking at this NIST atomic spectral database. We could go in there, we could put an element like our mercury lights, and put mercury in there, the visible spectrum, 400 to 700 or 800 nanometers, hit go, and we get this huge table, and we get these lines. Now, when you went through and looked at the mercury light with the CHEM spectrometer, did you see the 5 lines? Yeah, there's a violet, a kind of a blue-green, a green, a yellow, and a red. And sure enough, we see all of those right here. And those are what we're seeing. If you were to take a computer software and go along and like where you see those peaks, if you had an emission line that went up and down based on the intensity, that's what you would see. That would be the spectrum that you would see. So your eyeball's doing this right here. It's just not giving you numbers, but it's measuring the spectrum of mercury when you look at these mercury fluorescent lights. Okay. And for those on the camera, I made this in graduate school. It's like a 50 cent piece of diffraction film, and I cut the corner out to make a slit. So you can make your own at home if you can get some diffraction film. You can find some diffraction film in these little fireworks glasses. So go find you some fireworks glasses and you can make a CHEM spectrometer. Okay. Now, we looked at the Grotrian diagram last time where we looked at mercury and we realized, wow, mercury is kind of complex in that the lowest energy, actually the ground state, is the xenon core, 5d10, and there's a 4f14 in there too. 6s1, 6p1. So it's bumped an electron from the s orbital to the p orbital and relaxed. The atom has relaxed, and so it's dropped down quite a bit from what we would put in as the ground state. Let's see, for mercury would be that 6s2, 5d10, 4f14, completely filled. And so it's just bopped one of those electrons out of that 6s and put it in the 6p. Now that, using the Aufbau filling scheme, we would not predict that as being the ground state. But clearly, having those 2 electrons in the s orbital is higher energy for a big atom like mercury. So giving that electron an independent subshell to be in, the 6p, gives those electrons independent views of the nucleus. And so then that somehow causes the whole electron cloud to drop in energy, and we end up down here in the ground state. Okay, you could put it in the 7p or the 8p or the 9p and still be below what we would predict as the Aufbau filling scheme ground state for mercury. So then we look at the spectral database for these spectral lines, and here's the spectrum that we have that we can see with the CHEM spectrometer, and we can see the most intense peaks here. Now you get hundreds of possibilities for this spectrum of this atom, but you can look in this in relative intensity column and you can see the strongest peaks. So here's an 1100, a 240, and a 4000. So 435.8335. That's this one right here. 435.8335 nanometers. And it's very accurate. We know what, how the actual center of that peak is. Of course, then there's an 1100 at 546. So that's this one right here. 546.0750. And then there's a 250 at 576. So right here, that's 576. And then this big peak, this big red peak is not shown here because that is actually an Hg plus line. So it's the mercury cation. So this is going from Hg2 plus an electron gives Hg plus, and light comes out. Okay. So when that electron goes onto the Hg2 plus in the gaseous state, then you get the pachinko game where it's bouncing down through all the levels and it's giving off the emission spectrum of the mercury cation. This is the table, the emission table for mercury neutral. The physicists, man, they really screwed it up, because if you go into this previous screen and you put in the term here, you can't just write mercury. You got to write in mercury 1 for the neutral. That's what idiots the physicists are. Right? They should have put mercury 0, right? They put mercury 1, it confuses us chemists, because mercury 1 is a mercury cation, but not on the physics atomic spectral database, okay? I mean, they did a lot of work, and I applaud them, but man, this is confusing to a chemist, right? So Hg1 on the ASD is neutral mercury. So then this is the spectrum. You'd have to type in Hg2, then you'd get the table for the mercury cation, and then you would see this emission here at the 600 and looks like 630 or so, 630-ish, okay, for the mercury cation. Then you would have the intensities and the center peak, the centers of those peaks. You could even use a high-resolution scan of something simple like this fluorescent tube light to calibrate your visible spectrometer, because we know the exact wavelengths of those lines. And so if your spectrometer was off a little bit, you could correct it in terms of wavelength by using the atomic spectral database. And that's one of the major uses of the NIST data, is to calibrate our instruments. And most of your spectrometers, store-bought, are calibrated at the factory. But you never know. If something breaks, you maybe need to move if you move the grading on some of these diode array spectrometers, you're going to need to recalibrate, and this would be a good source for those center wavelengths. But as we look at this table, we see these couple of columns called terms. What are these terms? They're called term symbols. Okay, and we saw that in the Grotrian diagram for helium. All across the top, we saw these term symbols. And this is the reason we need those term symbols, or this is the way what it allows us to distinguish between these two. If you notice on the left side of this Grotrian diagram, we have the electron configuration 1s, 2s, and then over here we have the same one, 1s, 2s. So what's different about those two setups, those two electron configurations? Remember that a configuration is a larger collection of individual ways to build the atom. So those individual ways we call permutations. So that's all like statistics and probability language. So there's a configuration, and then inside the configuration are individual permutations. Think about how all the different ways we can put together a 1s and a 2s. So we could do, let's just do this, 1s and 2s. So we've got a line like that. We could do an electron up, an electron up. We could do 1s, 2s, where we have an electron up, an electron down. 1s, 2s. We could have an electron down, 1s, 2s. We could have an electron down, an electron up. Are there any other options? I don't think so, as long as we keep it just 1s and 2s, okay? So notice how the multiplicity, this one, the spin is plus 1/2 and plus 1/2. And so the overall spin, S, is equal to, the sum of that is equal to 1. So 2s plus 1 is equal to 3. So that's a triplet. And this one also, both spins are down. And so we're going to have essentially the magnitude of that spin is 1 again. And so that would also be a triplet. So this is a triplet. Here, the spins are paired. And so that's going to be a singlet. And here the spins are paired. So these two are singlets. So you see the individual permutations, the way we had the spins in here will give us situations where we have triplets and where we have singlets. And so that's what's separating this electron configuration. Again, all 4 of these cases have the same electron configuration of 1s, 2s. But the individual ways you do the spins and put electrons in those two orbitals, those are called permutations or microstates. And so then we have to distinguish between these permutations, and some are singlets and some are triplets. So let's look at those term symbols that go along with these things. Okay, so the term symbols help us distinguish between these identical electron configurations, because otherwise it's confusing. We have 1s, 2s, but there's more to it than that. We have to put electrons in those orbitals. So the mathematical sets on the following pages, and we're going to be doing a lot of little sets where we have a maximum value and a minimum value and integer differences in between. These only deal with electrons in unfilled shells. So that's a governing principle. If the shells are filled, we don't worry about them. It's only those last valence electrons that are in unfilled shells. The term symbols for ground state atoms with filled subshells are all singlet S0. So look at all of these. We have beryllium, magnesium, calcium, that whole group. That's all an S2 group. And so everything's fulfilled. Even if it's calcium, you have the argon core, which is a P6 is filled, the 3s2 is filled, the 2p's are filled, 2s's are filled, and the 1s's are filled. So everything's filled up. There's no unfilled subshells. And so that's going to be a singlet S0 term. Okay, so that's the sort of the default term. And so let's talk about this Clebsch-Gordon series. This is how we come up with those different term symbols for the unfilled subshells. And so we have this capital L, the total orbital angular momentum. And again, just to emphasize, it's electrons in unfilled subshells only. We do them pairwise. Now this gets really tedious if you have three electrons. Like look at nitrogen. We have a P3 situation, 2P3. Okay, and this looks like it only deals with L1 and L2. These are the angular momentum quantum numbers for two of those electrons. The way we would do this is we would do all of the pairs for the first two electrons, and then for each of those terms we would add in the third. And I'm not going to ask you to do one of those because it's a nested problem and it just gets way longer. Okay, so we're just going to do two electrons pairings. Okay, but if you do a third, then it would be, you would do this full set and then you would start adding in another electron to each of the terms in this set. So let's just do the two ones. You'll get an idea for how these angular momentum values are coupled together. So then you have the multiplicity, the 2s plus 1 multiplicity. And so you got to come up with s to calculate the multiplicity. So this s right here is this set of s's. And so these would be the s, little s or m sub s. Sometimes they're listed as m sub s. So for the electrons, the magnetic quantum number. Okay. So this would be like plus 1/2, etc. for those electrons. Okay, and then there's J, the total angular momentum quantum number. And this, we're going to be using the scheme of Russel-Saunders coupling. So that's just a vocabulary word for you. This is the type of coupling we're doing. Okay, where it's L plus S. So notice how the problem builds on itself. We first come up with a set of L values. So L is this set of L values. Then we have a set of S values. And then the J values depend upon each term in the L plus S. So this problem cascades. We come up with the capital L's, then we come up with the multiplicities, and sometimes we split those into like triplets and singlets, and then for each of those terms we have J values. You're not going to learn anything by looking at this page, so let's learn by doing. We'll do several of these, okay? But this is how you make the term. That multiplicity piece is shown right here, these little superscript prefixes, okay? The multiplicities go right here. Then you have the capital letter for the L term, and then the little J values go as a subscript suffix. So let's practice, okay? So here's our All right, let's do the simplest one. Let's just pick a single electron system. So we'll do the terms for sodium. Okay, since we're doing just a single one, we're not adding L1 and L2. We just have L1 because we only have one electron. Okay, and so we've got to look to see what is the angular momentum quantum number for that one electron. So this is the angular momentum quantum number right here, and that is right there. That's the S. So whenever we're doing this, I don't know how you are, but I always come up with little mnemonics, little ways to always remember how to do things. Even if it should be something that I should know, I still have a little procedure for determining those things so I don't make a mistake. So what does an s orbital look like? It looks like a fist, right? An s orbital looks like a fist. And a fist, how many fingers am I holding up if I have a fist? 0, okay? So it's SPDF. So SPDF. L is 3 for an F orbital. If I have an S orbital, 0. P orbital, 1. D orbital, 2. F orbital, 3. What's after F? G is 4. So L is 4 for a G orbital. Okay. And so H would be 5. So that's how I do it. If you're looking at me and I'm taking a test and I'm doing term symbols, just so I know I don't make a mistake on my little lowercase l's, I got a D orbital, an electron in a D orbital, I go S, P, D. That's 2. L is 2. Okay. So don't be afraid to back yourself up with some simple little things like that. So I got an S orbital, that's L equals 0. Okay, so there's my L value for this. Now, again, we go back, 0 is an S, so we're going to use a capital S for this electron. So this term is a capital S, okay, and this is case sensitive because the electron is in an S orbital, L equals 0. Okay, then we talk about the spin. So the little s or the m sub s, again, some books have m sub s here, is equal to 1/2, okay, for a single electron. Now, you may say, but wait a minute, what if it's spin down, right? This electron could be spin up or it could be spin down. Always assume that they're all spin up in doing these. So that all of the s's, if I have 2 electrons, I have a plus 1/2 and a plus 1/2, and I'm going to add those up because I'm going to calculate the maximum and the minimum values. So we're going to start with the maximum value of plus, and then we'll subtract 1 all the way down to where we get to the difference of those. So the Clebsch-Gordon series is coming up with all of the possibilities of all the spins. That's what this whole series thing is doing. So we always just start with plus up, plus 1/2 and plus 1/2 for the 2 electrons. And then when we do the Clebsch-Gordon series, we're calculating all the other permutations. So that's what this series is doing. But we only have 1 electron. It's a plus 1/2. So when we calculate the multiplicity, it's 2 times 1/2, which gives us 1, plus 1, which is 2. So it'll be a doublet. Okay, so we know that our term is going to look like this. It's going to be S with a 2 up here. So this is our term. Now we need to calculate the J values, right? So the J values will go down here. L plus S is the max value. So we start out with the maximum. And then we subtract 1 from that maximum, and then subtract 1, and then subtract 1, all the way down until we get to the minimum. So we always calculate the maximum first, the minimum second, and then fill in the middle. Start with the maximum, then the minimum, then fill in the middle. So our maximum is 0 plus 1, okay? And it goes down to the absolute value of 0 minus, or plus 1/2 and 0 minus 1/2. So this is going to be a minus 1/2 absolute value. So that's also equal to plus 1/2. So the maximum value is 1/2. The minimum value is 1/2. And so there's nothing in between there. So we only have one J value. It's 1/2. I try to make this easy by starting with a single electron, but it's almost so easy that it gets confusing. We don't have anything in our sets. We just have a set of 1 for each of these values. We have only one value for the capital L, 0. We only have one value for S, which is a half, and we only have one value for J, which is also a half. Okay, so we only have one term in the ground state electron configuration for sodium. We just have a doublet S 1/2. So our ground state would be labeled with that term symbol. Okay. Now, if we're going to do spectroscopy, this electron can hop up into other orbitals. So let's do one where this electron is in the p orbital. And also this term will be the same. There's nothing in this whole series that has anything to do with the nucleus. Okay, so we don't know that this is required for a sodium atom. This could be any NS1. So this would be the same term symbol for lithium, potassium, rubidium, cesium, etc. The whole group 1A would have the ground state configuration of doublet S 1/2. Okay, so let's do an excited state sodium atom, the NP1 system. So now the electron's in the p orbital, so sp, so that's L equals 1. So the term is a capital P. Then S 1/2, so it's still a doublet. Okay, but then we get to the J values, and now we've got something a little more interesting. We've got L plus S. So L plus S, that's 1.5, all the way down to 1 minus a half. So this would be plus 1/2 here for the minimum value. And so these are our two terms. And this is something I want you to get comfortable with. Whenever I have 1 plus a half, I can make that 1 the same as 2 halves. And so 2 halves plus 1/2 is 3 halves. And that's a common practice to just list it that way, as 3 halves and 1/2. And I can see that there's an integer of 1 between those two. 3 halves minus 2 halves is 1/2. And so that's my set of J values. So I have two terms for the excited state sodium, and that's the doublet P 3 halves and the doublet P 1/2. So the J value splitting would be hyperfine splitting. So this would be the ground state would be the doublet S 1/2, and the excited state where that electron's in the p orbital would be split, very small splitting of the doublet P 3 halves and the doublet P 1/2. So when we look at the spectrum, here's our energy level diagram. The ground state, doublet S 1/2, the excited state, doublet P 3 halves, doublet P 1/2. There's only 17 wave numbers between those two, or in wavelength, it's 589.76 and 589.16. So 0.6 nanometers difference in the spectrum. And so that's where this term doublet and singlet came from, was the spectral information. And so when we started seeing doublets in the spectrum, we started calling those states doublets, and then we got into the Clebsch-Gordon series and saw that there are ways of putting the electrons in these orbitals. Then that's why we have this doublet, is we have a split excited state, very small hyperfine splitting. So the J level splitting tells us the fine structure of a peak. Okay. And so used to, we had, I would guess, sodium contamination in these lights. You know, we like white light, and the yellowy light is, I don't know. It doesn't really bother me, but my wife, she hates it. She doesn't like yellow lights. She likes white lights. If we have sodium contamination in these mercury lights, it's more yellow. So they can kind of fine tune it by putting a little bit more or less sodium. And they pretty well scrub the sodium out of these lights. If you look up here, you don't see very bright yellow lines, okay? You do see some yellow, but if you were to take this spectrometer out to one of the yellow street lights, if you could still find one, and look at that yellow street light, you would be able to see 2 lines. It'd be really cool. And that tells you that this little cheesy spectrometer has a resolution of at least 0.6 nanometers resolution. So that's pretty darn good. Anyway, it's partly the density of the cells in your retina, gives you a high resolution, and then you can narrow the slit down. and this distance is pretty good too. So you can see, 0.6 nanometer spacing in this little cheesy spectrometer. Okay, so in the book and other books, they'll have often the ground state electron configurations. So you can look at this table and you can see what the ground state electron configurations for all of these systems are. And so you see for the S1, we had the doublet S, okay? And we just verified that for sodium. For the P1, we had the doublet P, and we verified that for sodium. Those are very simple. But notice as you get into more and more unpaired electrons, we get to the P2, and we'll do that one next. You see the P2 on the third level, we have 3 terms there. And that's for the ground state. It could have some excited states where you get more terms. But the worst situation is if you have like 5 unpaired electrons, because think of all the different ways you can have those paired up and unpaired or paired down and so on. And so you can see that when we get to D5, that's one of the most complicated cases. So we would do electron 1 and 2, come up with that series, and then every term in that series we would couple with electron 3. And then the next term we would couple with electron 3. So we'd have groups of series. So we'd have 4 or so groups of series, and then every term in those we would couple with electron 4, and then electron 5. And so look how many terms we have just in the ground state for a D5 system. It's crazy. I don't even know how long that would take. I've never tried it because I look at that, I just get intimidated. I'm like, no, I'm not even going to do that. And I would never require you guys to do that. And that's why we'd have physicists. They do the tedious work and then publish it all online. It's really great. But we'll do P2. So we can get to P2 or maybe an S and an F or a P and a D or something like that. So we'll do 2 electrons and you'll be comfortable with that. And once you kind of get a feel for how it works, the rest is the same. It's just more tedious. Okay, but you'll get an idea for how it works for 2 electrons. Okay. Now, one thing that's interesting too is this is weird. Let's look at the P5 and the P1. So this is telling me that boron and fluorine have the same term symbols. Okay, and that's kind of strange. So boron, right? Boron is 2p. We have 3 of those. Okay, and it's got 1 electron in the 2p orbital. And fluorine, 2p orbital. You see how there's really no chairs for this one here. He's got a chair over here, and then I could move it over to this one, and I had to move an electron over. And so how many places I can move this electron? Spin up, I can move it to 3 places. I could do spin down, move it to 3 places. Same situation here. So since I have everything filled except for 1, these are going to end up being the same term symbol. So the P1 and P5 are the same, and then the P2 and the P4 are the same. Okay. Same with the D orbitals, D1 and D9 are the same, and so on. So it's kind of interesting. Okay, so this small table gives the permutations within the ground state. Okay. For most of the elements on the periodic table. Notice I've bolded the ground state, just in your notes to sort of emphasize that. But the Clebsch-Gordon series gives you all of these plus the excited state. So let's do a P2 system for like carbon. Okay, so carbon's electron configuration, helium core, 2s2. So all of those are core electrons. They're all, not core electrons, but they're all filled subshells. We're only dealing with those last 2 electrons in the P subshell. So we ignore all of these. So we're just looking at the unfilled subshell. And I think I have a little circle around that. Yeah, they're only interested in those electrons in the unfilled subshells. So here's when we talk about L1 and L2. We have 2 electrons now. They're both in how we do the quantum number. So S, P. So it's a L of 1. So our max value, we got a 1 and a 1 right here. So max equals 2. And the min, 1 minus 1, min equals 0. So we're going to go from 2 down to 0 by subtracting 1. So 2 minus 1 is 1, so that's our middle term. And then 1 subtracting 1 is 0. We're down at the minimum term. Okay, so that's a P and a P minus a P. So again, this would be electrons both spin up, electrons then paired up, and so on. So our L values are 2 and 0 for the max and min, and minus 1 in the middle. So 2 minus 1 is 1, 1 minus 1 is 0. So then we come up with the capital letters for those. So again, 0 would be S, 1 would be P, 2 would be D. So that's where the D, P, and S came from. And so then we were able to, now we do the spins, okay? So this would be plus 1/2 and a plus 1/2. So that's going to equal 1, and then plus 1/2 minus 1/2. That's going to be 0. So 1 and 0, if I subtract 1 from 1, the maximum value, I hit 0, so there's no term in the middle. It's just 1 and 0. Okay. So those are the S values. And so when S equals 1, 2S plus 1 equals 3, and so that's going to be a triplet. And when S is 0, 2 times 0 plus 1 is 1, which is a singlet. And so this is going to be our set of terms. Without the J values, we're going to have a triplet D and a singlet D, a triplet P and a singlet P, a triplet S and a singlet S. So you see each one of these capital L's is given, and then each one of these multiplicities is given. So if we have 3 capital L's and we have 2 multiplicities, we have 3 times 2, we have 6 total terms. Okay, then we got to do the J values. So we do the L values and get the capital letters. Then we do the S and get the multiplicity. And then the last value, last practice or part of the procedure is the J, total angular momentum. So for each of these, remember J is L plus S. So for this one, like for this one right here, S equals 1, L equals S, P, D, so L equals 2, right? So we've got to pick a term and a multiplicity and do the J values for that one. Then we pick the next term and multiplicity and do the J values for that one. So we have to do 6 calculations next. Every term has a set of J values. Okay, so this is why this problem just is sort of like a pyramid. It gets more and more tedious. Now we have 6 terms. We got to pick each one of those and do 6 versions of the J calculation. So for triplet D, L equals 2, S equals 1. So remember that the J is L plus S for the maximum value, down to L minus S, absolute value. Okay, so that's the minimum. So we have 2 plus 1 down to 2 minus 1. And then, so our maximum value is 3. Our minimum value is 1. And so 3 minus 1 is 2. That's the thing in the middle. And 2 minus 1 is 1. We're down to the minimum value, so we stop. Okay, so there's our J values, 3, 2, 1. Now it's going to be summarized later, but we could write it out like this. We could write out a triplet D3, a triplet D2, and a triplet D1. So those are the J values for this D orbital. So one of the excited states is going to be up there, and it's going to have 3 little energy levels very closely spaced. That group of 3 is a triplet D, and one of those would be a J value of 3, a J value of 2, and a J value of 1, really close in energy. And so when we do a spectroscopic measurement, let's say we're starting in an S term, which has a single J value. We go up there, we're going to see 3 little peaks. There'll be 3 transitions, and there would be a triplet in the spectrum. And that's, again, where this came from, this triplet idea. We saw that in the spectrum. We're like, oh, there must be 3 levels involved here some way. And so that's why we call it a triplet. Okay, for the singlet D, okay, singlet S, that means S is equal to 0, okay, and this is L. So D, L is 2, S is 0 for the singlet. And so 2 plus 0 down to 2 minus 0, there's only going to be one term, that's going to be 2. And so then that's going to be the singlet D2 would be the way you would write that out. Okay, for the triplet P, L is 1 and S is 1. Okay, so L plus S down to L minus S. L plus S is 2, L minus S is 0. 2 minus 1 is 1, so then you get the term in the middle. 1 minus 1 is 0, so we get the full series of 3 values. And so that's going to give us the triplet P2, triplet P1, and triplet P0. Then for the singlet P, 1 plus 0, 1 minus 0 is going to be 1, and so it'll be singlet P1 would be that one. The triplet S, okay, this one is where the absolute value comes into play. So L plus S is 1, and sometimes students on the exam will go down to minus 1, but that's not right. It's absolute 0. So L minus S, so 0 minus 1 will be negative 1, but it's absolute 0, so it's also 1. So our max value is 1, our minimum value is 1, and so we only have one term. Some people put 1, 0, and minus 1, and that's not right. Okay, so this is just a triplet S1. And then our last one is the singlet S. So singlet S is 0, an S term, L is 0, so 0 plus 0 and 0 minus 0, that's all 0. So this would be the singlet S0. So here's all of the possible terms for a P2 system. Okay. So let's look at the atomic spectral database. Okay. Remember that table showed for a P2 system only a singlet S, a singlet D, and a triplet P. It didn't have a triplet D. It didn't have all of these other terms that we came up with. But look at the NIST atomic spectral database for carbon. The ground state electron configuration is 2s2, 2p2. So those 2 electrons are stuck in the 2p subshell, and it restricts some of the things that they can do. Okay. So this is true that the ground state electron configuration, again, configuration, has only those 3 terms. Okay. But then if we elevate one of those electrons to a 3p, then we get some of these other options. Okay. And why would that be? Well, remember that the 3p orbitals are m sub L equals -1, 0, and 1. And we could never have in the ground state configuration, if both of those electrons are in the 2p subshell, they can't both be +1/2 in the m sub L +1, for example, because that would mean they had the same 4 quantum numbers. They would have the same n, which is 2. They'd have the same s, which is 1, because it's the p orbital. They'd have the same m sub L +1, and they'd have the same spin +1/2. So there's some restrictions if they're in the same subshell. But if I take one of those electrons and put it in the 3p, it could be in the m sub L +1, and the 2p could be in the m sub L +1, but they have different n values, different principal quantum numbers. So they don't violate the Pauli exclusion principle, and that's what's coming up with some of these extra terms that are valid for excited states because they're in different subshells. So they could have the same m sub L quantum number because they have different principal quantum numbers. So that opens up some more terms for us, and we didn't have to worry about whether the electron was at m sub L +1 or m sub L -1 or m sub L 0. Why not? Because the Clebsch-Gordon series handles it for us. So some textbooks, if you get into this in the future, again, you'll see, maybe you're reading through the textbook, they want you to draw little pictures, and they have all the M sub L's, and you draw the pictures, and the picture version works for some simple atoms. That's how I learned it, but I learned to actually hate it, because how do you know if you've got all the pictures, all the possible pictures? Okay, this Clebsch-Gordon series, you're guaranteed to get all of the possible combinations, and it's very simple. It's a maximum value, it's a minimum value, you subtract one in between, you got the whole set. And then you take each of those terms and you do other sets. It's a procedural method for getting all of the terms, and you can see that it hits all of it. So we came up with all of these terms: the triplet D, 321, the triplet P, 210, the triplet S with just a 1J value, the singlet D with just a 2J value. All of those came out of our Clebsch-Gordon series, and we were able to come up with the terms for all of those possible combinations. So that's fantastic. Now, many levels can have the ground state configuration. So this is, again, a emphasis on the configuration. Notice how this configuration is 2p2, okay? But that's the ground state configuration, but there is only one actual ground state, okay? The lowest energy level is the ground state. That ground state has a configuration of 2s2, 2p2. Lots of levels can have the same configuration, but there's only one ground state. So just kind of emphasizing some of the terminology. And the Clebsch-Gordon series produced all of those permutations for the p2 electron configuration. We could do more complicated ones. Check the homework. Like, you could take this one, and let's say we excite this molecule, so it's 2p1, 3d1. Okay, so now you're going to have, different L's. You're going to have some more complicated stuff. So practice on that one. Practice on an excited state carbon atom, and come up with all of the possibilities for a 2p1, 3d1 electron configuration. Now, this applies to most of the periodic table, but as you get into the heavier, lower periods in the periodic table, you have to go to a different coupling scheme. So we did Russel-Saunders coupling. There's also pure JJ coupling. All right, y'all have a good day.